Let's take a look here at this example limit problem. We are taking the limit as x approaches 4 of this particular rational function, x squared minus 4x divided by x squared minus 3x minus 4. Now, if you've been following the notes in the reading, you know we have a direct substitution property where if we have a polynomial or rational function and x is approaching some number in the domain of that function, we can simply substitute it in directly. So let's take a look and see if that applies here. X is approaching 4. If we, in order to see if this is in the domain of this function, we would plug that into the denominator and make sure that we don't get 0. So we have 4 squared is 16. 3 times 4 is 12. 16 minus 12 is 4. 4 minus 4 is 0. That, unfortunately, means that we cannot use the direct substitution property. If we try plugging that in, we have division by 0, which is undefined. That doesn't give us an answer. Now, you might wonder if, well, maybe that just means the limit doesn't exist. And that's possible. Let's take note off to the side here of what I did here. So in the denominator, we got 0. Let's take a look at the numerator. Plugging in 4 into the numerator. 4 squared is 16. 4 times 4 is 16. 16 minus 16 is also 0. Okay. Now, 0 over 0 is what is known as an indeterminate form. By itself, it's undefined. But when it arises in these limit problems, when a form like this arises in limits, very frequently, we can actually find a value for the limit. Not always, but we frequently can. If this numerator had been non-zero, and the denominator is going to 0, then that suggests that we have a vertical asymptote, and you could try some of the things that we looked at in the previous section. But knowing that this is 0 over 0, maybe it has a vertical asymptote, or maybe it's just a hole and there's actually a limit. So we'll have to do some other sorts of things here. It's important if you're figuring these things out and maybe you have some intermediate work to keep track of what you're figuring, you keep that cordoned off to the side. This is not, this limit is not equal to 0 over 0 or anything like that. This is just some little scratch work to try to figure out what structure does this have? What does it resemble? We see, oh, it has the form. The numerator is going to 0. The denominator is going to 0. That means that we need to do some algebraic manipulations to this. There are several different kinds of manipulations we might do, and learning which ones are appropriate when is largely a matter of experience. But with polynomials, if we're taking a limit as x is approaching a finite value, and we have a ratio of polynomials like this, and we have a 0 over 0 form, often one of the first things to try is factoring. So the numerator, we see there's a common factor of x, so let's pull that out. Whenever factoring polynomials, look for a common factor first. In the denominator, there are no common factors, but this is a quadratic trinomial, so we can try setting up a factorization here. 4 can be split into 1 and 4 or 2 and 2. 2 and 2 is not going to give us a 3, so we have the 1 and 4. We need opposite signs. The greater one negative, so it looks like we get something like this. Double check, x squared minus 4x plus 1x minus 4. Looks good. So this expression is equal to this expression, so the limits are equal. Now you might notice here, we have these common factors of x minus 4. And your natural impulse is hopefully to cancel those out. And we can do that here, but we have to be careful to understand why we can do that here. Okay. Because canceling those out is only possible when they are non-zero. Okay, let me go ahead and write what we get when we cancel that out, and then I'll talk about it. So when we cancel those, it reduces down to this. Now, this initial function, x squared minus 4x divided by x squared minus 3x minus 4, and this function, x divided by x plus 1, are not identical functions because they have different domains. This first function is not defined at 4, whereas this last function here is. Now, outside of 4, as long as x is not equal to 4, then these two functions are equal. Okay? But they are technically different functions, so we have to be careful of that. The reason we can cancel this here is that we are taking the limit as x approaches 4. And remember that when we're evaluating limits, we don't actually care what the function value is at 4. We're asking what it does when x is near 4, but not equal to it. That means when we're evaluating a limit as x approaches 4, we can assume for any algebra we do that x is not equal to 4. Since x is not equal to 4, x minus 4 is a non-zero number, and that means that x minus 4 divided by x minus 4 equals 1. And we can reduce this down to x over x plus 1. Now that we have that, we have simplified this, so let's take a look back from the beginning. We have that direct substitution property. 4 is in the domain of this function, and that means that by the direct substitution property, we can simply say 4 over 4 plus 1, and that means that the limit is equal to 4/5. So we had some algebraic work to do up front. Once we simplified this, the final evaluation of the limit was fairly straightforward. And remember that direct substitution property is really just a shortcutting of application of the limit laws, right? From this expression, we could say, okay, well, we have a limit of a quotient. And our limit law number, number 5, the denominator is not approaching 0, so law number 5 allows us to say that this is the quotient of limits. It would be the limit of x over the limit of x plus 1, then we can use our sum law to split that up, and blah, blah, blah. We do the substitute, we take x going to 4, we get this. We're just skipping a couple of steps of writing down the limits and getting to this 4/5 here. Okay. Note that we would not be able to apply the limit laws to this original expression because this is a limit of a quotient. And the limit law dealing with quotients stipulates that the limit of the denominator cannot be 0. But in the original expression, the limit of the denominator is 0. So even our limit laws won't help us there, and we need to do some other sorts of manipulations. But yes, a little bit of algebra and some careful reasoning allows us to work this limit out pretty quickly. You can check this on a graph, for instance. If you graph this on a calculator or computer, if you do something like what I talked about previously and do like a zoom decimal on a graphing calculator, you will see the little gap at 4. But if you zoom in on it or use the trace feature, you will find that when you're very close to 4, the function should be close to 4/5.